Okay, this video covers section 2.6, which is all about related rates. And this is going to be kind of an extension of what we did last time in 2.5 with implicit differentiation. So take a look at the notes that I have here. It says you've seen how the chain rule can be used to find dy dx implicitly. Another important use of the chain rule is to find the rates of change of two or more variables that are changing with respect to time, giving us expressions such as these. Notice how the denominator of each of these is a dt. So basically that would mean that it's with respect to time. So dy dt means the derivative of y with respect to time, or the derivative of x with respect to time, or the dv is probably going to represent the derivative of volume with respect to time. Okay, so here's the idea. Let's say we have this kind of a conical shaped paper cup, you know, like you'd see at a water fountain or something like that. And the idea is, suppose that you've got water in this cup, but notice it says it's slowly leaking. So I've got all of this water in the cup, but I don't know, maybe there's, you know, like a little tiny pinprick hole. So the water just starts to leak, right? So at a certain point, maybe the water level is down to here, right? You know, and you'd probably be getting to have a little bit of a puddle down here, right? And then maybe after some more time, the water level is way down to here, you know, maybe with a much bigger puddle. I don't know. Okay, but the idea is as the water goes down or as the water leaks out, there's a lot of things that are changing. Well, for one thing, the volume of water in the cup as you go through changes. So we would say the rate of change of the volume with respect to time. Another rate of change that is changing is if you think about when you look in the cup, you see that kind of circular shape, right? The surface of the water would be a circle. Well, that radius of that circle as the water level goes down, isn't that radius of that circle getting smaller? So we could say there's a rate of change of the radius with respect to time. Another thing, as the water level goes down, think about the height, or in other words, how high the cone is filled, right? Won't the height of that water get smaller and smaller as the water leaks out? So that would be like the rate of change of the height. So there's a lot of different factors or different variables that are changing based on time. Okay, so we're going to first of all talk about kind of the calculus, the algebra behind it, and then we'll turn it into more of an application. So I want to find dy dt, not dy dx, but dy dt of this particular equation. Now once I do that, I'll plug all this stuff in, but how do I find a dy dt? Well, remember when we did dy dx, every time we took the derivative of a y term, we had to put that little dy dx. But really, I was kind of leading you astray. It wasn't just because it was a y. It was really because it wasn't an x. So it's all about what's in the denominator right here. That's the variable that we're taking the derivative with respect to. So that's the one that really matters. So here's the idea. I would start on the left. If I take the derivative of y, well, it's just a 1, right? But it's like a 1... and then I just took the derivative of y with respect to t, not with respect to x. Okay, equals, keep going. Well, the derivative of 5x squared, yeah, that's going to be 10x. But this time I need to write, I just took the derivative of x with respect to t. So basically, any variable that's not a t is going to need one of these little notations on it. Keep going, minus the derivative of 6x is 6, but I just took the derivative of x with respect to t, and then the derivative of 2 is 0. So there's my setup. So notice I've got a dy dt and a dx dt. So the question is, well, what do they want me to find? Well, look at the directions. They want me to find dy dt, basically when x is 4, and dx dt equals 2. Well, if I'm trying to find dy dt, do I have everything that I need? Well, dy dt is going to equal 10 times x they told me was, what they tell me? X they told me was 4. And dx dt they said was 2 minus 6. There's dx dt again. So if we do the math, let's see, what is that? 40, 80 minus 12. 80 minus 12, what is that, 68? I don't care that much about the math. I care more about knowing how to handle this derivative. Okay, so I can take the derivative of any variable with respect to any other variable. Okay, so let's turn these into application problems. Well, there's kind of a process. And what I find is at first, you get overwhelmed because you see all the words. But as you start doing these problems, you'll see that you do the exact same thing every time. Yes, we're definitely going to draw a picture if possible. But here's kind of something I really want to point out. Always go through and start listing your given information. And probably the most important thing is also write down what you're trying to find. So many people don't do that, and then they come to me and they say, I don't know how to get started. Well, the reason you don't know how to get started is because you don't know what you're trying to find. That always tells you how to get started. Okay? Keep in mind whether or not your rates of change are positive or negative, right? That's important. And then basically, we'll kind of follow these other steps, but let me take you through a particular problem as we go through those steps. Okay, so look at my first example. It says a pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. Okay, so I have some kind of a circle here. And it says the radius of the outer ripple. So let's talk about, this is the circle of my outer ripple. It says that the radius, so here's the radius, is increasing at a rate of 1 foot per second. Okay, the radius is increasing. So the rate of change of the radius with respect to time equals 1 foot per second. And since the circle is getting bigger, or the radius is getting bigger, it's definitely going to be a positive 1 foot per second. When the radius is 4 feet, so r equals 4, find, there it is. What am I trying to find? Find the rate of change, the rate at which the area is changing. So we're trying to find the rate of change of the area. So find dA dt. Okay, so I said it's all about what you're trying to find. Well, if I need to find a dA dt, I have to have an equation that has an a in it that I can take the derivative of. Well, we're talking about a circle, right? So what is the area of a circle? Well, the area of a circle is pi r squared. So in my description above, after I've written down everything I'm trying to find and what I'm given, notice number 3 says, find an equation that relates the variables. Well, the equation is all about what you're trying to find. If I want to find dA, you need an equation that has an a. Okay, so now I'm going to take the derivative with respect to time. So the derivative of a would be dA dt. On the other side, remember pi is a constant, so leave it alone. The derivative of r squared would be 2r, but I just took the derivative of r with respect to time. Okay, so I took the derivative, and now the question is, well, if I'm trying to find dA dt, do I have everything else that I need? Well, dA dt is going to equal 2 pi. R we know is 4. dr we know is 1. So what are we going to have here? 8 pi, and usually they're going to want units. Since this is an area, I'm going to say it's square feet, and since it's a rate of change, it's per second. Okay? Okay, let's do another example. We normally spend 2 days on this rate of change concept, and usually problems like example 3 come in on the second day, so I'm going to do that example last and go on to example 4. I know this one comes in, I think, on both days. Okay, so here's the idea. It says a 13-foot ladder is leaning against a wall. So like I said, we're going to draw a picture if we can. So I'm going to say here's the wall on the ground, and there's this 13-foot ladder that's leaning against the wall. Okay, now that ladder is 13 feet long, and it's not changing. It's not like the ladder is changing, from 13 feet to 12 feet or whatever. It's just a 13. Suppose that the base of the ladder, I'm going to say that this is the base of the ladder. Suppose that the base of the ladder slides away from the wall, so it's sliding this direction at a constant rate of 3 feet per second. So I'm going to say that this bottom side of the triangle, I'll call that B for base. If the ladder is sliding away, then that side of the triangle is getting bigger. So when they say it's sliding away at a rate of 3 feet per second, I'm going to say the rate of change of B with respect to T is 3 feet per second, right? And it's positive because B is getting bigger. Now think about it. If that side is being pulled away from the wall, then at the same time, this side is going to be sliding down, right? I'm going to call this side H for the height. And it says, how fast is the top of the ladder sliding down the wall? So they want me to find the rate of change, because it says how fast. So I want to find the rate of change of the height with respect to time. And think about it, since that side of the triangle is getting smaller, once we find this value, it better be negative, right? Because if the side's getting smaller, then the rate of change should be negative. What else do we know? It says when the base of the ladder is 5 feet from the wall. So we want this at the moment when B equals 5. Okay, like I said before, always look at what you're trying to find. If I need to find a dH dt, I need an equation that has an h in it. Right? So if I look at this triangle, I see a right triangle. Wouldn't the Pythagorean theorem have an h in it? And yeah, it would also have a b, but that's okay because I've got lots of information about b. So I'm going to use the equation, the Pythagorean theorem. So I'm going to say h squared plus b squared equals 13 squared. Now notice I used the 13 because that side was not changing, but I did not go ahead and plug in the 5 for b yet because b is changing, so I can't plug it in until after I take the derivative. Okay, so let's take the derivative. So the derivative of h squared would be 2h, but just took the derivative of h with respect to time, plus derivative of b squared would be 2b, but just took the derivative of b with respect to time, equals the derivative of 13 squared is 0. Now, I know I'm trying to solve for dH dt, but do I have everything else I need? Well, 2 times, I know, do I know what h is? I mean, I know b is 5. Well, look at it. If we know that b is 5, couldn't you do a Pythagorean theorem and find h, right? In other words, wouldn't h squared plus 25 have to equal 169? So h squared is 144. Look at that. H must be 12, right? And if you recognize that as a 5, 12, 13 triangle, you might not even need it to do the Pythagorean theorem. But, so now we know h is 12. dH I don't know, but that's okay, because that's what I want to solve for in a minute. Plus 2 times b we know is 5, and dB we were given as 3. Okay, we're on the home stretch. If I want to solve for dH dt, I'm going to, let's see, this is 30, so I'll subtract that. And then I'm going to have to divide by this 24. So what is that going to be? Negative 5/4. And this was the height, so it would just be feet per second. And notice it did turn out to be negative because, like we said, the height of that triangle is getting smaller. Okay, but you see we did the same thing. We wrote down what we were given, what we're trying to find. We started with an equation, took the derivative, and then just plugged everything in. Okay, let's see if this one follows the same pattern. Notice it says, a fish is reeled in at a rate of 2 feet per second from a bridge that is 16 feet above the water. All right, so here's the water, and there's this bridge that is 16 feet above. So here's my bridge. So my guy is standing, right up here, and he's reeling in this fish. Okay, so here's my fish. I don't know, what does a fish look like? Something like that. I have no idea. Okay, there's this fish that is getting reeled in, and so he's got his fishing line attached to the fish. Now, when it says that the fish is reeled in at a rate of 2 feet per second, the question is, what side is it that they're talking about? If the fish is being reeled in, well, as he's reeling him in, he's not pulling the fish up this line, but the fish is being pulled along the level of the water, right? So I'm thinking maybe if I call this side X, it's X that is my dx dt. Let's see if that'll work for us. So dx dt, the rate of change of x, is 2. Now, let's see, is that a positive 2 or a negative 2? Well, isn't x getting smaller as I reel in the fish? So I think it would be a negative 2 feet per second. Let's see, the bridge is 16 feet. Notice the bridge is not changing. It's going to stay 16, so that's not a variable. At what rate is the angle between the line and the water? Okay, here's the angle between the fishing line and the water. I'm going to call that theta, since it's an angle. At what rate is the angle changing? So I want to find the rate of change of the angle. So find d theta dt when there are 20 feet of line out. Okay, well, if there's 20 feet of line, isn't that the hypotenuse? But as the fish is being reeled in, that line is getting smaller, right? So I'm going to call the hypotenuse, I'm going to call it, I guess I'll call it h for hypotenuse. Okay, and so I'm given that h equals 20. But keep in mind, h is a variable because it's changing, right? We're doing this at the moment when it's 20, but it's changing. All right, so if I'm trying to find d theta, I need an equation that has a theta in it. Well, luckily, you've had pre-calculus. Couldn't we just pick a trig function? Now, I could use any of the trig functions. Here's what I'm thinking. Why don't we pick a trig function that uses the 16, because the fewer variables, the easier my derivative should be. And I'm given dx dt, so why don't I pick a trig function that uses x and 16? So there's my angle theta. Wouldn't that be tangent? So what if I say tangent of theta equals opposite over adjacent, right? 16 over x. So I'm ready to take the derivative. The derivative of tangent is secant squared theta, but I just took the derivative of theta, so it's a d theta dt. And think of that 16 over x, think of that as 16 times 1 over x. So wouldn't the derivative be negative 16 over x squared, right? We know that the derivative of 1 over x is negative 1 over x squared. And since it's an x, we need a dx dt. Okay. Do we have everything we need? I don't have x, but I could find x, couldn't I? Since I know that h is 20, if I want to find x, I could do a Pythagorean theorem. But I'm thinking, if both of 16 and 20, if those are divided by 4, that would be 4 and 5. So doesn't that mean x is going to come out to be 3 times 4, 12? Again, you can do Pythagorean theorem and check me, but I'm pretty sure it is. Okay. But what I still don't know is secant theta. I need to know what secant theta is. Well, look here. Look at my triangle. Isn't secant, let's see, I know that cosine is adjacent over hypotenuse, which would be 12 over 20. So doesn't that mean secant of theta would be 20 over 12, or if we reduce it, what is 2 will be 10 over 6, so 5 over 3. That makes sense? Okay, so secant is 5 over 3. That means secant squared would be 25 over 9. D theta we don't know. And then I have negative 16x is 12. So I'm just going to write that right now as 12 squared. And then dx dt is negative 2. So I'll put negative 2 right there. Now, I know you're thinking, oh, I'll put my calculator, but you guys, sometimes if you do just a little bit at a time, it's easier to just not even use your calculator. So if I'm trying to solve for d theta dt, on the other side, I will cancel the negatives. On the other side, I had 16 times 2, and I know that's 32, but I want to show you something. On the bottom, I have 12 squared. I'm just going to write it as 12 times 12. And if I want to get rid of this 25 over 9, couldn't I multiply by 9 over 25? So couldn't I do some simplifying here? Let's see. I could say 3. How about I do 2 into 12 6 times? I could say 3 goes into 6 2 times, and 3 into 9 3 times. And actually, I could say, hey, this 3 is going to go into this 12 4 times. And then I could say this 2 goes into this 16 8 times. Oh, wow, I found more. 4 goes into 8 2 times. So what do I have left? On top, all I have left is 2. And on the bottom, all I have left is 25. So there's my answer. But let's talk about units. Let's see. In trig, we always use radians. In calculus, we always use radians as opposed to degrees. So for theta, I'm going to say it's going to be radians per second. There it is. Okay. I'm going to leave that right there because, like I said, usually it's day 2 when we come back and do this cone type problem. So we'll do that example. We'll save that example for next time.